I wanted to make a video to discuss the integration methods from chapter 3, and so I wanted to first kind of just review those methods and talk about when to use each one, because on the test you're going to have a section that looks much like the first problem on the written practice exam, where you have a bunch of integration problems and you need to decide which integration method to choose, and then you need to integrate. So if I'm looking through the test and I get to problems like these, the first thing I want to say is, okay, can I use U-substitution? Can you use U-substitution? And in order to determine if it's a U-substitution problem, you first need to have two functions, but you want to kind of decide for yourself if those two functions are related in the fashion that you would need for a U-substitution. So let's say, here's the question: do you have two functions that are related where one of the functions is a composition of two functions? Remember, we usually want to let u be the inside function in that composition of two functions. Okay, so that's for a U-substitution. Now, if they're not related, if those two functions are not related, then you're going to want to use integration by parts. So integration by parts is when you have two unrelated functions. So do you have two unrelated functions? And remember, if that's the case, then you're going to use Lipit, or some of you may like Liate, to help you determine what to pick for U and what to pick for DV. So those are the two methods you use when you have two functions. Now, what if you don't have two functions? Well, then it's going to fall into some of those other types. So you could have trig integrals, and those typically are going to have powers of sine and cosine, or powers of secant and tangent. So you could have your integral is going to look something like the sine of x to a power times the cosine of x to a power. Or it could look like the integral of secant of x to a power tangent of x to a power. So anytime you have something that looks like that, you're going to want to use the trig integral methods. Fourth, you could have a trig substitution. Trig substitution. A U-substitution, but trig substitution. And that's usually the case when you have your integrand. That's what you're taking the integral of. Your integrand has a 1 minus x squared, or the square root of a 1 minus x squared, or the square root of x squared minus 1, or the square root of x squared plus 1, or it could just be x squared plus 1, or it could be, say, the square root of x squared minus 9, or so there's a whole bunch of different ways they could look, but they're going to look something like that. They're going to have that in the integral, or something like that. And then fifth, we could have a partial fraction problem. This is the last type. Partial fractions. Remember, partial fractions look like when you have the integral of something that looks like p of x over q of x, where both p of x and q of x are polynomials. An example of that could be something like, say, x plus 2 over x squared plus 3x plus 2. So that's a ratio of two polynomials. So then you're going to use partial fraction decomposition. So let's go ahead now and jump into this practice exam, and let's see if we can decipher which method to use. So I'm looking at A here, and I see right away, we have two functions. Now, the first question you're going to want to ask is, are they related? Where we could use a U-substitution, or are they not related? So go ahead and think about that for a second. And hopefully, what you decide is that they are not related. And in order for it to be a U-substitution, we would need this to be like a squared. Because if it was squared, then we could let u be negative 0.6 y squared. And then du is going to be negative 1.2 y dy. And we could solve for dy. dy would be du over negative 1.2 y. And that y there would cancel with the y here. But because it's not y squared, we're not going to get that cancellation going. So we can't use a u-sub in this case. So we're going to have to do something different. If the two functions are not related, then we're going to need to use integration by parts, right? So that's the idea here. We want to use integration by parts, and we want to use Lipit. And there's two types of functions we have here. We have a polynomial function. That's the y function. And then the other one is the exponential function. Exponential function is the e to the negative 0.6y. And so if we do that, we have that u, remember the first thing we see in Lipit is going to be our u. So u is going to be y. And we have dv is going to be e to the negative 0.6y, and then du, the derivative of y is 1 dy, and v, if we take the antiderivative, we have a little mental substitution there, so we have to divide by negative 0.0 or negative 0.6. We have e to the negative 0.6y. So remember, the integral of u dv equals uv minus the integral of v du. So we have uv, we have negative 1 divided by 0.6. And when we divide by 0.6, that is, I'm going to make this look. That's 5/3. So this right here is negative 5/3 e to the negative 0.6y. So we have negative 5/3, and we also are multiplying by u. So negative 5/3 y e to the negative 0.6y minus the integral of v du. So minus a negative 5/3 e to the minus 0.6y dy. This is going to be, both of these have to be evaluated from 0 to 5, right? Because we have a definite integral. And so this is negative 5/3. And then we can plug in 5, and we're going to get 5 e to the minus 3 minus 0. Then our integral is a minus a minus 5/3, so that's going to turn into a plus 5/3. So we have a plus 5/3. And then again, we're taking the antiderivative e to the minus 0.6y. So that's e to the minus 0.6y. And then we're going to divide by minus 0.6, which is like, we're going to divide by minus 0.6, evaluating between 0 and 5. We have minus 5/3 times 5e to the minus 3. That's actually going to be what? That's going to be minus 25 over 3e to the minus 3. And then our next part, we have 5/3 divided by minus 0.06. If you take 5/3 divided by minus 0.6, that's going to give you what? That's going to give you 25 over 9. So this is minus 25 over 9 times e to the minus 3 minus e to the 0, which is 1. And if you combine this, well, let's distribute first, actually, I guess. So we have minus 25 over 3 e to the minus 3, minus 25 over 9 e to the minus 3, minus plus 25 over 9. So this gives us a final answer of 25 over 9 minus 100 over 9 e to the minus 3rd, combining like terms. All right, so that's the first one. Let's look at the next one. So we have the integral from 1 to 4 of dt over dt plus 1 to the 3rd. And so this does not have two functions, but it does have a very simple function inside of a function. So this is an idea that we're probably going to want to use a U-substitution here, because we could let u be 2t plus 1, and we know this works out nicely because the derivative of that is just 2. We get the dt. So we just get a factor of 1/2 because dt equals du over 2. And so we can rewrite this, right? We get 1 over u cubed, and in place of dt, we have du over 2. We can change our bounds. When t equals 1, we have 2 times 1 plus 1 is 3. And then when t equals 4, we have 2 times 4 plus 1 is 9. So our upper bound here is going to be 9. So yeah, this is just 1/2 times the integral of, treat this as a power, right? U to the negative 3 du from 3 to 9. So that's B. I'm going to let you finish that one. C, okay. Do we have two different related functions or unrelated functions? No. But what we do have is we have a power of sine and cosine. And so if you recall with these ones, we want to usually take our odd power and we want to peel it off. So we want to take and rewrite this as sine squared times cosine squared, and then that extra sign we're going to write here at the end. And then we can just use a substitution because we can let u be the other function. So let u be cosine, which means du is going to be negative sine theta d theta, and that's our part over here. That's our part that we peeled off, right? So, except that it doesn't have the negative, but that's all right. We just take care of that by putting the negative out front. So we're left with sine squared theta, and then the cosine squared is going to become u squared, and then we have du. The only problem is we have this extra sine squared, but remember, sine squared theta plus cosine squared theta is equal to 1, which means sine squared theta is equal to 1 minus cosine squared theta. So that's just 1 minus u squared. So really, we can replace that with 1 minus u squared and then distribute. So we have minus the integral of u squared minus u to the 4th du. That's what we get when we distribute in this u squared. And so that becomes pretty easy to evaluate. Only thing we want to make sure we do is change our bounds. So I'm going to let you go ahead and finish that one. I'm going to move on to D here. So right away, hopefully you're noticing, oh, we have a partial fraction problem, right? We have one of these where we have something over something where the top and the bottom are both polynomials. Now the top is just 1, but that's okay. We do need, though, in order to do partial fraction decomposition, we need to be able to factor the denominator. So when you factor it, you're left with, what do we have, y minus 6 times y plus 2 dy. And so we can take that 1 over y minus 6 times y plus 2, and that should be rewritten as a over y minus 6 plus b over y plus 2. And you can go ahead and do that one from there. Remember, I just want to point out that if you do happen to have a numerator with a higher power than the denominator, you have to perform division first, long division first, to simplify that fraction. All right, we can keep going here. Take a look at E. So E, we have two functions, right? Are they related or are they unrelated? Well, to me it looks like they are unrelated functions. So we're going to want to go ahead and use which method? Are we going to use U-substitution or integration by parts? I'm going to use integration by parts. And so we have, again, Lipit. Which one does x to the 3 halves fall under? Well, that's the polynomial one. So that's x to the 3 halves. And then we have natural log of x. That's our log one. So we want to let u equal the natural log of x. That's the first one. And then we want to let dv equal x to the 3 halves. So when we take the derivative, du equals 1 over x dx. And then we take the antiderivative, we add 1 to the power, that becomes x to the 5 halves, and divide by 5 halves, or multiply by 2/5. And so this becomes, we have u times v, so we have 2/5 times x to the 5 halves times the natural log of x. And we have minus the integral of v du, so minus 2/5 times x to the 5 halves times 1 over x dx. And x to the 5 halves over x, that's just going to be x to the 3 halves. So this is the integral of x to the 3 halves, because this is 1. So when you subtract those powers, 5 halves minus 1 is like 5 halves minus 2 halves, which makes 3 halves. And we have to use the power rule to evaluate that. And so we get what? We get minus 2/5. And then again, we've already done this one. It's x to the 5/2 times 2/5. Plus c. And you can simplify that a little bit and get to the answer that was in the solution, but that's a bit more or less how we're going to do this. All right, so now we move on to f, and you can see with f, ding, 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 right away I see the square root of the x squared minus 1. That's making me think right away trig substitution, right? Whenever you have that square root of x squared minus 1 thing, we want to do trig substitution. And when it's the x squared minus 1, that's a giveaway that we're going to want to use secant theta as our substitution. And the reason why is because when you plug that in, you get secant squared theta minus 1. And remember, secant squared theta minus 1 is equal to tangent squared theta, right? And the square root of tangent squared is tangent. Square root of tangent squared is tangent theta. Of course, we also need to find dx. dx, the derivative of secant, is secant tangent. And so we can now do our substitution, right? We know the top, we just saw that simplifies to tangent theta. And the bottom, that's x, so that's going to be secant theta. And then we know dx is secant theta tangent theta, d theta. And changing our bounds, actually, I'm just going to go ahead and leave our bounds off for now. And we can go back to it at the end because we know we're going to need to do that. So what can we simplify here? So secants can cancel. And we're left with what? We're left with tangent squared. So we have the integral of tangent squared theta d theta. And it's not necessarily obvious right away, but remember, we just used when we were simplifying the square root, we used the fact that secant squared theta minus 1 is equal to tangent squared theta. So this is the same as the integral of secant squared theta minus 1. And the reason why that would be advantageous is we know the antiderivative of secant squared, right? What's the antiderivative of secant squared? That's tangent theta. So we have tangent theta, and then the antiderivative of negative 1 is negative theta. And then we need to go back to be in terms of x, right? So we need our right triangle. We know that secant theta, right here, we know secant theta is equal to x, and so the reciprocal of that, it would be cosine theta, which would be, and the reciprocal of x is 1 over x. So cosine theta, that's adjacent over hypotenuse, is going to be adjacent over hypotenuse, 1 over x. Then this side over here is going to be the x squared minus 1. And so tangent theta is going to be the square root of x squared minus 1 over 1. Right? Do we need the over 1 though? Not really. And then theta is going to be the inverse secant of x. Right? So right here, theta is going to be the inverse secant of x. Or it might be actually even easier to use this one and say theta equals the inverse cosine of 1 over x. When we do that, minus the inverse cosine of 1 over x. Now that we're back to x, we're going to evaluate this between 1 and 2. So going ahead and plugging those in, we have, plugging in 2, we have 2 squared minus 1 is 4, minus 1 is 3, so we have the square root of 3 minus the inverse cosine of 1/2. Well, where is cosine equal to 1/2 at? Well, that's pi over 3. And then when we plug in 1, we get the square root of 1 squared minus 1, which is 0, minus the inverse cosine of 1, right? 1 over 1 is 1. Inverse cosine of 1, well, that's equal to 0. So this is going to be just root 3 minus pi over 3. So that's that one. All right, moving on to G. Well, this looks like powers of not sine and cosine like the earlier one we did, part C here, but powers of secant and tangent. So looking at that, we're probably going to want to recognize, we're probably going to want to have U be tangent, which means du is going to be secant squared theta d theta. So we're going to want to peel off a secant squared. This is going to want to become, let me write this over on the side here so it's out of the way. So if u is equal to tangent theta, then du is equal to secant squared theta d theta. So this is going to want to be rewritten as secant to the 4th over tangent squared times that extra secant squared theta d theta. And the reason why my giveaway that it's going to go that way is because your tangent is in the denominator. So the alternative is that we could let u be secant theta, but then du would have to be secant theta tangent theta. And our tangent theta, though, is in the denominator. It's not on top. So that's going to make things difficult. So let's see if this works out. If this is the case, then we're going to have to convert secant to the 4th to also be in terms of tangent. So remember, up above we use secant squared minus 1 equals tangent squared. Well, that means secant squared theta is equal to 1 plus tangent squared theta. So that means when we have secant to the 4th theta, that's like secant squared squared, and secant squared is 1 plus tangent squared. So instead of secant squared squared, we can write 1 plus tangent squared squared. And when you square that, you get 1 plus 2 tangent squared plus tangent to the 4th. All right, so basically what I'm saying is all that stuff right there, that's equivalent to secant to the 4th. And that gets everything in terms of tangent, which is important because our u is tangent. And so instead of secant to the 4th up there, we can rewrite that as 1 plus 2 tangent squared plus tangent to the 4th. That's going to be 1 plus 2u squared plus what? Plus u to the 4th over u squared, right? Times secant squared theta d theta. Well, that's just du. Right? This is just du. And then you may have never done this before, or it may have been a while since you integrated something like this, but what I would do here is just split this apart. You could also do long division if you wanted, but to me I think it's easier to just make this the integral of 1 over u squared plus 2u squared over u squared plus u to the 4th over u squared du. Because then this simplifies to u to the negative 2 plus 2 plus u squared. And of course, then we can take the antiderivative. So we have what? We have, you add 1 to that power, you get negative 1, divide by negative 1, we get negative 1 over u. And then we get plus 2u plus 1/3 u cubed plus c. And u is tangent, so this is minus 1 over tangent theta plus 2 tangent theta plus 1/3 tangent cubed theta plus c. And 1 over tangent is cotangent, so this is minus cotangent theta plus 2 tangent theta plus 1/3 tangent cubed theta plus c. All right, so we got that one. The next one again is, hopefully you recognize that rational form, so that's going to be a problem where we're going to want to use partial fractions. Numerator does not have a higher degree, so we can just go ahead and jump into this, but you do need to factor the top, right? Or the bottom, I mean. The bottom, you have to factor out an x squared, which leaves x plus 3. And so when you go to write this, when you go to rewrite this, when you have x squared plus 8x minus 3 over x squared times x plus 3, we have a quadratic factor, or I'm sorry, a repeated linear factor. So that repeated one is going to be a over x plus b over x squared, right? And then we have plus c over x plus 3. So you can go ahead and finish that one. Then looks like we have one more here, and notice again it's got that square root of the x squared plus 1, so that is trig substitution, right? Trig sub. And what are we going to let x be for this one? X is going to be tangent theta. Dx is going to be secant squared theta. And so our square root of x squared plus 1, that's going to simplify down, right? Because that's going to be square root of tangent squared theta plus 1, the square root of secant squared theta, which is secant theta. So here we get secant squared theta, if x is tangent theta, then the square root simplifies to secant theta, we have our d theta. Should have a d theta on it. We're almost done. This can be rewritten because secant will cancel with one of those. So we get the integral of secant theta over tangent theta d theta. And so this integral that we get here is not one that I would ever expect you to have to do. This is not something we really know how to do. And so I'm going to change this problem actually to make it something that's a little bit more realistic. So instead of x here on the bottom, why don't we go ahead and put x on the top? And so that's going to change. Instead of a tangent theta on the bottom, that's going to leave a tangent theta on the top. And so we're going to get left with a, what? We're going to get left with integral of secant theta tangent theta, right? D theta. And we know that the antiderivative secant tangent is just secant theta. Plus C. And we can then use our right triangle. There's theta. You know, tangent of theta is equal to x over 1, which makes this square root of x squared plus 1. So secant theta is, we know cosine is adjacent over hypotenuse, so that means secant theta is going to be hypotenuse over adjacent. So that's going to be square root of x squared plus 1 over 1 plus c, or just the square root of x squared plus 1 plus c. And that's our answer. We got one more to look at here. That's going to be J. And J is not super obvious either. This is not something I would necessarily expect you to do on the test. So I'm going to help you with this first step. So sine of 2x, there's an identity there that says that that's equal to 2 times the sine of x times the cosine of x. So we can rewrite this as the integral of cosine cubed x times 2 sine x cosine x. Then we can pull the 2 out, and we can go cosine to the 4th x times sine x dx, and you can do a trig integral there. So I'm going to go ahead and stop this video right here. I hope that you found this helpful. Please let me know if you have any questions about any of these problems or any of the other problems as you're studying to prepare for your test. Thank you.